computer. All right. So in order to do what we're trying to do today, we're going to do some prime factorization first. But before we can do prime factorization, we might need a few definitions maybe. And that first definition is prime number. Right? What is a prime number? No, that's not the number of Amazon Prime packages you get each day. Prime number. What is a prime number? Most of you probably already know what a prime number is. Anybody?
Yeah.
Andrew?
A prime number is basically any number that can't be divided.
Except
for by itself.
Yes, a number that can only be divided by one and itself. That's correct. So if you don't know that definition, maybe write it down. A number that is only, keyword there being only, because every number we can divide by one in itself, most numbers anyway, only divisible by one and itself. So a prime number is a number that's only divisible by one in itself. So let's start with numbers. Let's start with like 0. Is 0 a prime number? Yeah. 0 is actually not a prime number. Is 1 a prime number? Yeah. 1 is actually not a prime number. So 0 and 1 are neither prime nor the opposite of prime. You might know what the opposite of prime is? Yeah, it starts with a C. Good. Composite. Yeah, composite. So 0 and 1 are neither prime nor composite. Here's why. You actually can't divide by 0. Actually can't divide a number by 0. Try it in your calculator. It's not going to work. It's going to give you like domain error. You can't divide by 0. And why is 1 not prime? 1's not prime because, like, yes, we can divide by 1 in itself, but 1 in itself is the same number. And if 1 in itself is the same number, then it's not really prime. All right. So what are some prime numbers? What about 2? Is 2 a prime number? Yeah, 2 is a prime number. I can only divide by 1 and 2. There's no other number I can divide that by evenly. What about 3? 3 is prime. What about 4? 4 is not because we can divide by 2. What about 5? What about 6? No. 7? 7 is prime. 8? 9? 10? 11. All right. We'll stop there, but there are more, but that's probably all the ones that we're going to need in this class. So we want to take a number and write it as the product of only prime numbers. This is called the prime factorization. And this is not what we're doing today, but it's going to help us with what we're doing. So this kind of review from like 5th, 6th grade maybe. And maybe you use the factor tree method. With the factor tree method, we're going to start with 120. You can read the directions there if you want. I'm not going to read them to you, but I will go over each step, but I'm not just going to read them to you. So we put the number on the page. We find any 2 numbers that we can multiply to get that number.
Wait, I had
Yeah, that's my bad. When I was cutting these in half, that sheet was not supposed to be in there. So what 2 numbers, any 2 numbers that we can multiply to get 120? 60 and 2. It doesn't matter which 2 we start with. Maybe you started with 10 and 12. Maybe you started with 40 and 3. Maybe you started with 30 and 4. It doesn't matter what numbers we start with, as long as they actually multiply to give me 120. Now, 60 and 2, are either of those 2 numbers prime? No. 2 is a prime number, so we're going to circle it. So if we're using this like tree metaphor, like we have a tree, we have branches on the tree, and at the end of the tree, if we get to a prime number, that fruit is ready to be picked. So 2 is our fruit that we're going to pick here in a little bit. Is 60 that prime? No, so we got to keep going. So at this point, it doesn't matter what 2 numbers we use, as long as they multiply to give me 60. 6 and 10 would work. 15 and 4 would work. 20 and 3 would work. It doesn't matter. Are either of those numbers prime? If they are, we're going to circle them, but they're not. So we got to keep going. What can we multiply to get 6? 2 and 3. Are those prime? Yeah, so we're gonna circle those. Those are right. They are ready to be picked. What about 10? Is 10 prime?
No, 5 and 2.
5 and 2, so we're gonna circle those. We get 2 and 5.
I didn't above it.
So now prime factorization means we can write this number as a product multiplication of just prime numbers. So 120 would be equal to all of these numbers that we've circled multiplied together. So I'm going to put them in order from least to greatest. 2 times 2 times 2. There's 3 of those. There's 1 3 and there's 1 5. It doesn't matter what numbers we started with. The numbers that we circled would all be the same. Doesn't matter that I started with 60 and 2. We could have started with any numbers and we would have ended up with the same 5 numbers circled. The other method that you probably didn't learn, maybe, is called the birthday cake method. It does the same thing as the factor tree method. I don't care which one you use. I'm going to show you this one, but you probably won't use it if I'm being honest, because you've never seen it before today. The factor tree method and the birthday cake method are really, really closely related. But the main difference is that when I do the birthday cake method, if we call it that, I have to divide by a prime number. I can't just pick any number to divide 120 by. I actually have to pick a prime number. And a prime number is 2. So I would just divide by 2 until I couldn't divide by 2 anymore. So 120 divided by 2 is 60.
That's the hard one.
60 divided by 2 is 30. 30 divided by 2 is 15. So I kind of went a little quick there, but all I did was divide by 2 until I can't divide by 2 anymore. And notice how what we're building kind of looks like a birthday cake. That's why they call it the birthday cake method, because it kind of looks like a birthday cake.
So then 15 times 2 times 2 times 2 would equal.
15 times 2 times 2 times 2 would equal 120, but 15 is not a prime number, so we got to keep going. 15, what can we divide 15 by? But it has to be a prime number if we're using this method. 3, and 3 times 5. And then 5 is a prime number, but birthday cake is not finished until we have a candle on top. So our candle is going to be the 1 on top. So we would divide by 5 as well, ended up with the 1 on top. So our prime factorization, the prime numbers that we can multiply together and get 120 would be these numbers right here. So all the numbers on the outside would be our prime factors. And if you notice, they are the same as what we got for the factor tree method. But what if we divided by a number that wasn't prime? You might put like 4 times 2 times 3 times 5. Well, 4 is not a prime number, so it technically wouldn't be prime factors. So it is important that if we're going to use this method, you divide by prime numbers like 2, 3, 5, 7, 11, etc. Okay, cool. So that's just kind of a review of what we might need. So our goal today is not actually prime factorization. So according to our table of contents, I'm now on page 2. And I don't have a copy of printout or anything for page 2. So maybe what you just wrote down was on the front of the page. Maybe you just want to flip over to the back and write this on the back. Not on the back of the sheet I gave you, because you're going to glue that in your notebook. And if you write on the back of this and then glue it in your notebook, are you going to be able to see what's on the back? Probably not. So put that on page 1 and then just flip it over to page 2. Because what we're about to write, probably it might fit on the back of this if you write small, but it's not going to fit on the rest of your paper. If you need paper, you can top drawer. It's about 4,000 sheets of paper in that top drawer. You're welcome to as many as you need. But we are on page 2 now. And we are simplifying square roots. We are simplifying square roots on page 2. Have you simplified square roots before? Yes, in Algebra 1, you learned how to do this. And your teacher said, hey, you can't use a calculator on this. And you were like, why can't I use a calculator? Well, they're trying to prepare you for maybe like the SAT, because guess what? The SAT has 2 reading sections and 2 math sections, I think. I think there's 4 sections total. Guess what one of those math sections is? Non-calculator. Okay, you can't use a calculator on half of the SAT for the math problems. So like half of the math problems, you can use the calculator. The other half, you don't get to use a calculator. And I would anticipate that one of these questions that we're about to see would be on that non-calculator section. Can you type these in your calculator? Yes. Can you type them in the calculator for my class? Sure, I'm not gonna tell you you can't use a calculator. But maybe you wanna go to college, maybe you have to take the SAT one day. Maybe it would benefit you to learn how to do this without a calculator. So I'm gonna show you how to do this without a calculator. You should maybe remember it from Algebra 1 though. So step 1, prime factorization. Hence why we went over prime factorization. Prime factorization. Step 2, we're going to circle pairs of the same number. Gonna circle pairs of the same number. So maybe we did our prime factorization for 120. Remember, we had like 2 times 2. So we would circle that pair, and then we had another 2 times 2, I think. We would circle that pair. So anytime we have the same number twice, we're going to circle those numbers. And number 3. Number 3, we're going to take the square roots of each pair. Going to take the square roots of each pair. And this will all make sense when we do an example in just a second. Can you just type this in your calculator? Absolutely. Will you get the right answer? Sure. Will you get full credit? Sure. But you might not know how to do it on the SAT. So let's talk about how maybe we might want to do one of these in this class. Or maybe on the SAT without a calculator. Maybe we had something like the square root of 48. I'm not interested in what the decimal number for that is. We're interested in the exact value equivalent of that, in which there's no perfect squares left inside the square root symbol. Like, what are you talking about? Well, let's work it out and make more sense. So square root of 48. Square root of 48. The first thing we want are the prime factors. So what are the prime factors of 48? Any 2 numbers that we can multiply to get 48. It doesn't matter which 2.
12 and 4.
12 and 4. I think I heard 2 and 24 first, so I'm going to use that one. But again, it doesn't matter which one we pick. When we get done circling numbers, we'll all have the same amount of 2s, the same amount of 3s. If we have a 5, we'll have the same amount of 5s. What's 24? What can we multiply to 24?
6 and 4.
6 and 4. If you use 2 and 12, guess what? That's okay. It doesn't matter. What can we multiply to get 6? 2 and 3. We're going to circle those. What can we multiply to get 4? 2 times 2. So we should have 4 2s. Everybody should have 4 2s and 1 3. It doesn't matter what numbers you pick, okay? As long as they multiply to give me 48. All right, so square root of 48 is equal to the square roots. 48 is 2 times 2 times 2 times 2. 2 times 2 times 2 times 2 times 3. 4 2s and a 3 multiplied together. Now we're going to circle pairs of the same number. We're going to circle pairs of the same number. So 2 times 2 and 2 times 2. We're going to circle those. Why might we circle those? Well, what did we just create? We just created a perfect square. What do we mean by perfect squares? Those things that we just know the square root of. Like, what's the square root of 9? 3. Why is the square root of 9 3? Because 3 times 3 is 9. What's the square root of 25? 5. Because 5 times 5 is 25. Take that same idea. What is 2 times 2 really?
4.
2 times 2 is just 4. So I'm going to write the square root symbol here. What's the square root of 4? 2. So this 2 times 2 led me to a 2 on the outside of the square root. So we had 2, now we only have 1. And maybe like algebra 1, you were learning this and your teacher said, hey, we have 2. If we have 2 of the same number, we have one of the same one of that number on the outside. And you're like, well, why? Well, here's why. What's 2 times 2? 2 times 2 is really just 4. We took the square root of 4, and that's why there's only 1 2 on the outside. What is 2 times 2 here? 4. What's the square root of 4? 2. What about 3? What's the square root of 3? We don't know. It's just 3. So it stays inside the square root. And now if we have more than one number on the outside or more than one number on the inside, we're just going to multiply those numbers together. So we can multiply the 2 2's on the outside. 2 times 2 is 4. And we get 4 times the square of 3. So we have simplified this to a way that there's no perfect squares left inside the square root. We've simplified all of those out. Did you have just type that in your calculator? Yes. All right, try this one. And then we'll move on to one more thing. Let's do square root of 50. And let's put a 3 in front of the square root. At first, you're just going to pretend the 3's not there. And then at the end, you're going to take your answer. So our answer was 4. And you would just multiply the outside times 3. So try that one. And we will go over it together in about 1 minute, maybe 2, but it shouldn't take you terribly long. 50 is a pretty easy number to break down. 50 is a pretty easy number to break down. All right, 50. What can we multiply to get 50? 10 and 5. 10 is 2 and 5. Those are all prime numbers. You can write out as much as you want. If you can see this and you're like, oh, 5 times 5, that's a pair. So I know that's 25. The square root of 25 is 5. So I put the 5 on the outside. I skip all this other stuff I'm about to write down. Like, I'm okay with that. So we get 50 is 2 times 5 times 5. We circle the 5s. 5 times 5 is 25. The square root of 25 is just 5. So we're going to take that 3 that was already on the outside and just multiply it by anything else that ends up on the outside. And whatever's left on the inside just stays on the inside. And then we multiply the 3 and the 15 together. And we get 15 times the square root of 2. By hand. Now, do I care if you use a calculator in this class? No, I don't.
Oh.
So type that in your calculator if you choose. It will say 3. Actually say 15 square root of 2 in your calculator. Type it in just like it looks. 3 square root of 50. Just like it looks. All right, let's take this idea, which you learned in Algebra 1. Everything we've done so far, you did in Algebra 1 without a calculator because it was a part of the EOC that you didn't get to use a calculator on. So your math teacher made sure, like, hey, we're going to do these without a calculator. And you probably did a lot of prime factors. Maybe you struggle with your multiplication facts, but that's okay. Now, with a calculator, try to square root of negative 96 with a calculator. So if you don't have your calculator out, go ahead and pull it out. So far, everything that we've done so far today, you could have typed in a calculator. Can you use your phone? Desmos will not simplify it the way we want. So if you were to type like 3 square root of 50 in Desmos, it will give you the decimal. And we don't really want the decimal in this class.
It's not letting me see the five.
Yeah, it's saying no error. It's not letting you do it. So we're going to take something that was Algebra 1, and just by adding a negative, is going to make it Algebra 2. Like what? Like, what's going on here? Like, how can just this negative make it that much more complicated? And this is a problem that has existed for thousands of years. So I'm going to kind of explain to you why your calculator says error. And hopefully it'll make sense, hopefully. And I'm gonna try to use this equation, x squared equals -1. To try to explain why did your calculator say math error or domain error, whichever calculator you have, depends on what it said. So if I had this equation, x squared equals -1, how could we get rid of the squared and solve for x?
Square root.
Yeah, we could just take the square root of both sides. The squared and the square root cancel each other out. You learned that probably in algebra 1, maybe before algebra 1. And we get x equals the square root of -1. X equals the square root of -1. But what's the square root of -1 really equal? Let's talk about it. I asked you earlier, what's the square root of 9? You said 3. Why was it 3? Because 3 times 3 is 9. I said, hey, what's the square root of 16? And you said 4, because 4 times 4 is 16. What's the square root of maybe 36? 6, because 6 times 6 is 36. So this idea of square root, a number times itself has to equal the number under the square root. So we're looking for a number times itself that equals -1. And some of you said 1. What is 1 times 1? 1 times 1 is 1. Does that equal -1?
No.
No, so that doesn't work. So I think maybe some of you said -1. -1 times -1. What is -1 times -1? That's +1. So that doesn't work. -1 times 1 is the other option that we might think. -1 times 1 is -1, and we're like, almost.
But they're not the same number.
But they're not the same number, because the whole idea of square root, a number times itself. So guess what? That's not possible either.
Well, we could if you do like negative. No, wait, no, you can't. In one word, it's 30 negative.
So guess what? It's actually not possible if we're talking about real numbers. And every number you've encountered up till today, we call a real number. You're going to learn a brand new set of numbers today called the imaginary numbers. And you're like, what are imaginary numbers? Well, here we go. Ancient mathematicians, all the way back to like the ancient Greeks in like 5000 BC, they noticed this. They noticed it and they said, it's not possible. And then like the ancient Romans also noticed this and they said like, it's not possible. And the Chinese noticed this and they said, it's not possible. And all of these cultures realized that, hey, this is not possible. They came up with problems that looked like this and they were like, that's just not possible and we really don't know what to do with it. So then during the Renaissance period, when a lot of things started happening, like you had Leonardo, Donatello, Raphael, Michelangelo. No, those are not just the Ninja Turtles. Those are famous artists from the Renaissance period. You also have famous scientists during the Renaissance period, like Sir Isaac Newton, and a lot of other famous scientists, and a lot of really good things happened during the Renaissance period for art and science. But not only did it happen for art and science, if you study the history of math, you'll notice a lot of stuff happened during the Renaissance period for mathematics as well. And one of those things was this idea right here. The mathematicians during that time said, no, this isn't possible. But we want a way to represent this number that's not possible. And here's what they said. They said, hey, we're going to let the square root of -1 equal I. I was their notation for that. And they understood that, hey, this is not possible. Like, there is no number that we can multiply by itself and get -1. But we're going to represent this with I. And you're going to see tomorrow and Wednesday, tomorrow is Wednesday, tomorrow Thursday, that we can actually use I the same way we would use X. We can add I's together. We can add and multiply I's together. And we call this the imaginary unit. So why is your calculator giving you domain error when we type square root of -96 in? Because it's actually not really possible to figure out what that is. Because no number times itself will give you -96. So we have this imaginary unit. And if we were to plug I back in for x, if we were to plug I back in, we get I squared. I is just the square root of -1 squared. And what's going to happen to the squared and the square root? They're going to cancel each other out. And what's that equal? That equals -1. So here's what you need to know, like tomorrow. You need to know that tomorrow I squared is equal to -1. You need to know that tomorrow. And that kind of comes from that equation that we just did. So I is the square root of -1. I squared is equal to -1. And now we have this whole new number system that we're going to learn a little bit about this week called the imaginary numbers. We're going to learn a little bit about these imaginary numbers. And where do they come from? They come from this idea right here that this is not really possible. So now let's go back and let's talk about this idea. The last example that we're going to do together today, this square root of -96. So no, your calculator won't do that. But is there a way that we can represent this using that imaginary unit I that we talked about today? And the answer to that is yes, there is a way. The square root of -96 is the same as -1 times 96. -1 times 96. You okay with that? -96 is just -1 times 96.
Yeah.
There's a property of square roots that says we can pull this apart and make this into two separate square roots. -1 times the square root of +96. We can just separate those. And just separate those. Now, what is the square root of -1? That number that we said doesn't really exist. It's just I. So now we have the square root of -1 is just I times this positive square root of 96. Now, how can we simplify the square root of +96? You can use your calculator and you can just type in +96, square root of +96. Or if we were to do this by hand, very quickly, I'm going to do this by hand. We would do a factor tree, 2 and 48, 2 and 24, 2 and 12, 2 and 6, and 2 and 3. So we have 1, 2, 3, 4, 5 twos, and 1 3. So this would be equal to I times the square root of 5 twos, 1, 2, 3, 4, 5, and a 3. And we would circle pairs of twos. 2 and 3 doesn't have a pair, so we end up with I times the square root of 4 is 2, the square root of 4 is 2, and we have a 2 and a 3 left over in the inside. So without a calculator, this is what it would look like. I'm okay if you use the calculator. And now we can multiply the things on the outside together and the things on the inside together. 2 times 2 is 4, and 4 times I is 4i. And 2 times 3 is 6. If you don't want to write it that way, you don't have to. As long as it looks like an I, it doesn't matter. And then we could put the I. Some people write the I in between the number and the square roots. Some other books, websites, videos, will put the I at the back. Which one's correct? They're both correct. They both mean the same thing. It doesn't. We're all multiplying. It doesn't matter what order we multiply in. But you need to know that those two things are equal. There's one worksheet I give you, the answer key might look like this, and then Delta Math might look like this. I don't know, right? But these are the same. So had you typed the square root of +96 in your calculator, you should have got 4 square root of 3. 4 square root of 6. And then what could you add to your answer? An I. So if you have a calculator, very quickly, let's do this. The square roots of -84 in your calculator. Preferably with your calculator. You can do it by hand if you don't have a calculator. Can you type square root of -84 in your calculator? No, but you can type square root of +84 in your calculator. And when you type square root of +84 in your calculator, what's it say? 2 times the square root of 21. If this is a question on a quiz, test, quick check, and you put 2 square root of 21, you will not get it right. Because the square root of a negative number implies that it's imaginary. So you have to put the I on your answer.
Like,
Okay, I'm understanding.
You have to put the I on your answer.